All right, here we are back for more discussion about aldehydes and ketones for Chem 2. Just a reminder at the top, I have a picture of the carbonyl group. Again, it's kind of turned sideways, but here we have the partial positive and partial negative end. This is a carbonyl group. We have our lone pair here. So we have an electron dense area, and that leaves the carbon end electropositive. All right, so the properties of aldehydes and ketones, boiling points. Going to follow kind of the similar trends as alcohols, a little bit different though, in that the boiling points are not going to be affected by hydrogen bonds because there are no hydrogen bonds with the other aldehydes and ketones, because up on the oxygen, you don't have a bond between an oxygen and a hydrogen, nitrogen, oxygen, or nitrogen, fluorine, etc. The oxygen is bonded to the carbon, so you have no hydrogen bonded to nitrogen, oxygen, or fluorine. So you do have a polar molecule though. So as always, you do have London dispersion forces. Those occur within all molecules. And because it is polar, you have dipole-dipole forces existing here. So the boiling points are going to increase with the length of the chain due to the fact that there's more electrons, and as you increase the number of electrons, you're going to have more dispersion forces. And between the aldehydes and ketones, remember the ketones have an additional alkyl group, another R on them, so they are going to be slightly higher. So the ketones are going to have a boiling point slightly higher than the aldehydes because they have an additional carbon atoms. So remember, you have for an aldehyde, you have an H on the one end because the carbonyl group is at the end, so it kind of ends it, and so you have lower molar masses, less electrons, so you're going to have less dispersion forces. In the grand scheme of things, if you were to put all of our functional groups that we've learned so far together, at the very end with the highest boiling points, we're going to have our alcohols. That's because the alcohols have the OH group, and that's going to have hydrogen bonding on them. Then we have our ketones. Then we have our aldehydes. And again, those have the carbonyl groups with the lone pairs. Then we're going to have our ethers that have the oxygen in there, but without those oxygen is within the carbon chain. And then at the very end, we will have our alkanes. Down at the bottom here, we have a table with just some examples to compare. If you notice here, the molar masses are very similar. So you have 58, 60, 58, 60. But we have an alkane, an ether, an aldehyde, and an alcohol. And the difference you have in the intermolecular forces, the IMFs, you have a van der Waals only, van der Waals, that's what VDW is standing for there, and weak dipole forces in the ethers. You have strong dipole forces in the aldehyde. They don't have an example of a ketone here. In an alcohol, you have van der Waals forces, you have dipole forces, and you also have hydrogen bonding. So you can see the differences in the boiling points here. So alkanes, boiling point of -1, all the way up to an alcohol, you'd have to have a temperature of 97 degrees Celsius. All right, moving on to solubility. Solubility, again, same kind of thing here, except now with solubility, you have that carbonyl group. Let me draw it again. And I know a lot of times we draw it with just kind of like this, but really around that carbon you have the sp2, so we're looking at 120-degree angles roughly, and so most of the time you should be drawing it like that. But we form hydrogen bonds with the water molecules because you have those water molecules, so you have the hydrogen bonding, and you have this nice force of attraction there. So very soluble with the shorter chained aldehydes and ketones. So form hydrogen bonds with, again, water. The lone pairs on the oxygen of the carbonyl group. That's what I was talking about up here. Those lone pairs, along with the hydrogen. So it's this force of attraction right here of the hydrogen on the water. The decrease in solubility occurs as the carbon chain length increases. Generally, they say the cutoff is about greater than 4 carbons. So as this carbon chain gets larger, so if you have, a great deal of carbons in your chain as they get larger and larger and larger, and you have, a water molecule, it's going to be less capable of dissolving that substance. And the solubility is roughly the same as alcohols and ethers. And then the last thing that I wanted to add is just some kind of interesting stuff on the odors. Aldehydes and ketones kind of have characteristic odors, and aldehydes are kind of interesting that the lower members, meaning the smaller aldehydes, the smaller chains, have sharp, pungent, not very good odors. And then as you add more carbons, they kind of get more fragrant and have some more attractive odors. I know you can't maybe read here in the video, but in your notes maybe you can read them. But I thought I'd include some of these. In A, it says benzaldehyde is an oil found in almonds. So almonds. B, this is the smell of cinnamon. Oil of cinnamon. Here's vanilla. Here is an herbal odor. And here's trans 2 cis 6 nonadienol, which gives a cucumber odor. So, when you have the shampoo or the lotion and it's cucumber scented. That's how they give all those nice fake smells to things. If we were in class, we would be making some different chemicals that make smells. Kind of fun lab to do. All right, next we have ketones. So acetone is a famous ketone. If you have fake nails and you've taken nails off with acetone, you know the smell of acetone. It's also formed during metabolism of lipids in the human body, and levels, usually it's broken down in the body, but if you have diabetes, you are unable to keep that level at a minimum. and so the levels can get out of whack. And if they do get out of whack, sometimes they can be detected in the urine. And if they get extremely out of whack, they can even be detected in a person's breath. So there's also some other ketones that have characteristic smells. The artificial butter, this is the one, artificial butter smell. They add to different things. B is the odor of violets. So, for example, if you go to buy some candles or whatever and they have violet smell. Musk oil is C. So if you're purchasing some cologne or whatever, musk oil. And D, camphor. So insect repellents, camphor. And then finally, I just have a couple examples. Which compound in each pair has the higher boiling point? So A, you'd be comparing acetone and 2-propanol. And so acetone is the common name for a ketone. If you look it up, it is, oops, sorry. This is acetone. And 2-propanol is this. So very similar compounds. However, one is an alcohol and one is a ketone. And hopefully you know that the alcohol would be greater as far as higher boiling point. And I went ahead and looked these up, and the alcohol is about 82.6 degrees Celsius, and acetone is about 56 degrees Celsius. So we are correct if we say 2-propanol. In the next pair, dimethyl ether and acetaldehyde. I'm sorry, I'm having pronunciation problems today. Acetaldehyde. So one's an ether, one's an aldehyde. We would predict that the aldehyde would be higher than the ether. We can check by doing the structures. So dimethyl ether would be an O in between these two, dimethyl. And then if we look up their structures, did I look them up or look up their boiling points? Dimethyl ether is negative 24 degrees Celsius, and the aldehyde is 20 degrees Celsius, so we were correct that the aldehyde is greater. Number 2, butanal aldehyde versus butanol alcohol. So we should be predicting the alcohol. If we look them up, we get about 75 degrees Celsius versus 117 degrees Celsius. So that would be true. So aldehyde, alcohol. And finally, acetone versus isobutane. So we have a ketone versus an alkane. And we should have a ketone beaten it out. And the acetone is 56 degrees Celsius, and the alkane is negative 12 degrees Celsius, roughly. So the ketone should win out.